All right, so Unit 5 is what's called thermodynamics, and we're going to talk way more about what that means here in this particular video. So first thing, we're going to look at what temperature is. So temperature is a measure of how much energy particles in a substance have. So adding or removing energy usually changes the temperature, and that it's really looking at how much internal energy something has. So internal energy is the energy of a substance due to the motions of particles and the energy that results from how far apart they are. Really, the more they move, the more temperature they have. If you add energy, temperature increases. If you remove energy, the temperature decreases. So when something warms up, it's typically warming up because energy is being added. When it cools down, it's cooling down because energy has been released. Okay, heat, on the other hand, is the energy transfer. Because objects have a difference in their temperatures. Okay, so from a macroscopic view, from a large point of view, energy transferred as heat tends to move from an object of higher temperature to an area of lower temperature. Just like if you think of like electric potential energy, same basic idea. So heat is energy transferred, temperature is, okay, so the direction in which an energy travels as heat can be explained here. Okay, so energy transfers from something that has more energy still, that's warmer, to something that's cooler. Okay, and energy will be actually transferred till the objects have the same energy and same temperature. Okay, so atoms of all objects are constantly moving, so they're all going to have some internal energy because temperature is a measure of energy. All objects have some temperature. Heat is the energy transferred from one object to another. Okay, so temperature is the energy of something that's motion. Heat is that energy transferred between two objects. So you give off heat. Temperature is that energy inside causing things to move. Okay, and when energy is transferred, work is done. Work is transferring energy. Okay, as we talked about in the last unit. Okay, so when there's no temperature difference between a substance and its surrounding, no net energy is transferred as heat. So no work is really done on the object if the temperature remains constant, if there's no temperature difference. Okay, so heat is indicated by the symbol Q. And like heat like work is a transfer of energy, so the unit is joules. Okay, so this is a big difference between heat and temperature. So temperature, degree of hotness or coldness. Okay, increased when heated, decreased when cooled. Heat is just energy transferred from one object to another. So temperature is energy inside an object. Heat is energy transferred between objects. All right. So again, work is done when something interacts with something else, giving it energy. The bigger thing is the environment. So when an object interacts with its surroundings, an energy is transferred. So when work is done on an object, energy is added, heat is added. Okay, when work is done by the system to the environment, energy is released. Okay, so when you warm up, you're gaining energy, you're gaining heat, work is done on you. When you cool off, so like when you sweat and release energy, you are doing work your work is on the environment. You're transferring energy to the environment. So again, here we go. So if work is positive, the system does work on its surroundings. So when you release energy, you're doing work. The work done by you is positive. When the surrounding heats you up, negative work is done by you. Okay. So again, here we go when we show these situations. So surroundings, so energy added is greater than 0. Okay. You cause it to move, work is 0, or work is positive. Okay. If energy is added to the system, okay. All right, so like this one, if work is done on the system, and energy release is greater than 0. Okay. All right, so now, type of energy transfer that is due to atoms transferring vibrations is called conduction. So when you touch, when things heat, it's like when the burners turn down the skillet's handle, heats up due to conduction. So this energy that's transferred, the heat that's transferred, when you touch something, conduction is when you touch and transfer energy through touching. The other two are called convection and radiation. And we're going to show you a quick little video to show you the differences here.
In the summer, a car parked in the sun can get extremely hot. This internal energy can be transferred to you as heat. Where does that energy come from, and how is it transferred to you? The radiation from the sun warms the car. This radiation consists of both visible and invisible wavelengths of light. When you first touch the door handle, it transfers a great deal of energy to your hand where you touch it. Energy transfer by touch is called conduction. Conduction occurs between two objects that are in contact with each other or within a single object. When you open the door, a blast of hot air warms your face. The very hot air has risen up from inside the car and replaced the normal temperature air that was near your face. This is transfer by convection, when matter carries energy in fluid currents. Energy that is transferred as heat is always transferred by one of these three methods: radiation, conduction, or convection.
Okay, so again, conduction is when you touch and transfer energy. Convection is when fluids, typically liquid or gases, flow where hotter liquids and gases flow up. And as they go up, they release energy and cool off and fall back down. Radiation is energy given off over a distance, like the sun. Like if you're near a burner and you can feel the heat from a distance, that's radiation. Okay, so heat and work are energy, like I said, heat that's transferred to or from a system. So the system is really the object interacting with the environment around it. Okay. So this is kind of a big idea here. An object never has heat or work in it. It has internal energy, and that internal energy is determining the transfer of energy, which is heat and work. Okay, so that system is the particles that are interacting with the surroundings. Okay, and the environment is outside. Okay, so we're going to look at this little problem here. So if this gas expands, as shown in this little figure here, the volume of this is positive, and the work done by the gas on the piston is positive. So the work that's done by this gas is positive because it's getting bigger. It's pushing on something. Okay, work done by the gas onto the piston. Now, if this gas was getting compressed, there would be work done on the gas by the piston. But in this case, the work is done by the gas on this piston. It's going to expand the gas. Okay, again, yeah, if the gas is compressed, the volume decreases and the work done by the gas is negative. So positive work, the object expands. Negative work, the object contracts. Okay. So again, when the gas volume remains constant, there's no displacement and no work done. Okay, although the pressure can change during a process, work is done only if volume changes. Okay. So a situation in which pressure increases and volume remains constant is comparable to like a force that doesn't displace something, like if you hold a block above your head. Okay, there's no change of energy. Work is not done in any situation. Work is only done on something if there's some sort of change in energy. Okay, so if friction is taken into account, mechanical energy isn't conserved. So if we look at this, you decrease the car's energy as you go down because of friction. Okay, but the total energy of the whole system is consistent. It just changes different types of forms. So the principle of energy conservation, that energy isn't really lost or gained, it just changes forms, is what takes into account what's called the first law of thermodynamics. And the first law of thermodynamics is this. Delta U equals Q minus W. Okay, delta U is the change of a system's internal energy, so how much energy is in the system, is equal to the energy transferred to the system as heat, which is Q, minus the energy transferred to or from a system as work, which is W. So system's energy is equal to the energy transferred to or from the system as heat, minus the energy transferred to or from the system as work. Because energy and work will change the energy of an object. Okay. So this is big. So if there's no transfer of energy or heat, Q is 0. There's no energy. There's no heat in there. Okay. If Q is greater than 0, energy is added to the system. So if Q is positive, energy is added to it. If Q is negative, energy is removed from the system as heat. Heat's given off. Okay. If work is positive, work is done by the system. It expands. If work is negative, it's getting compressed, because this is work done by the system. It's positive. It's work on the system. It's negative. It's releasing. It's giving off energy. And W is equal to 0, and there's no work done. So a sample problem here. A total of 135 joules of work is done on a gas as it undergoes compression. If the total internal energy of the gas increases by 114 joules during the process, what is the total amount of energy transferred as heat, and has the energy been added to or removed from the refrigerant as heat? Refrigerant, things that cool things down like your refrigerators. Okay, so the work, the reason it's 135, is done on a gas refrigerant, so it's going to get compressed. So the work is negative 135. The change in energy, it says, is 414 joules. Okay, work is done on the gas, so the work has a negative value. The internal energy increases during the process, so the change in internal energy has a positive internal energy. And we're looking for the heat transferred. So this is what's going on. Okay, it's getting compressed. We're looking at what happens to the energy, the heat, when the internal energy increases by 114 joules. So here's our situation. All right. So we're going to use this. We're going to start with the law of thermodynamics equation, and we're going to rearrange it to solve for Q. Just add W to both sides. So Q is equal to heat is equal to change in energy plus the work. Okay. So heat is equal to work plus energy. Okay. So the Q is equal to negative 21. So that actually means it gives off 21 joules of heat. Okay. So the heat is given off by the object into the environment. All right. So now when we look at this transfer of energy, let's look at something called efficiency. You might have heard of this term before. How well basically how well an object takes one energy and turns it into another form of energy is efficiency. And something that is highly efficient takes most of the energy that's put into it and gets it out. Okay? Nothing is 100% efficient. Nothing takes all the energy in and converts it to usable energy out. There's always friction and other energy is lost. Okay? So that friction basically decreases the efficiency of an object. You look at like a vehicle. Most vehicles are under 50% efficient. Even the most highly efficient ones are like 80 to 90% efficient, where the 80 to 90% of the energy in is released out in some form of useful energy, like making the car move. Think of a car, you lose a lot of heat energy, lose a lot of sound energy, lose a lot of energy from the fuel to make it move. That's the equation that we don't have to worry about. Okay. The last thing on this is how fast you change energy. Okay, power is, by definition, power is how fast work is done to change energies. Okay, power is measured in watts. The faster the energy is transferred from one form to another, the more work that is done. Okay, it's like your light bulbs are rated in watts of power. The higher the wattage, the faster, like on your light bulb, the faster electrical energy is converted to light and heat energy. Okay. So there you go. That's your video for Unit 5. There is only one video for Unit 5. Answer the questions on the formative assessment, and we will see you in class.